I'm the Senior Principal Product Manager at OpenShift, so responsible for several things around container infrastructure, and networking is a very big one of those. So one of the things I want to talk about is, so what makes us a contributor to advancing Kubernetes networking? Well, there's a few different ways to explain how it is that we advance networking, but I think our curriculum vitae should explain that we actually have a pretty good amount of Kubernetes leadership that's in place for networking that helps drive not only existing projects, but brings new projects to the table within the Kubernetes development community on the behalf of customers that aren't necessarily Kubernetes experts. So we have a number of people that do a number of different things, and I almost hesitate to present this slide because this is really just scratches the surface of our Kubernetes contributions. But for example, one of the leads on our networking engineering team is an engineering co-lead for the Kubernetes Network Special Interest Group. As part of that group, he, for example, led and created and led a network plumbing working group that was joined by about 17 different vendors. So there was definitely a community effort there to develop the whole multi-interface pod project, which you've heard already from some of the speakers, and I'm definitely going to talk more about in many of my slides coming up. Lots of things. We represent about half of the CNI, the Kubernetes Container Network Interface Maintainers team. We represent about half of the IPv6 dual stack development effort. These are just some top of mind things. Kubernetes, we're contributors to Kubernetes Ingress version 2. Quick history lesson. We developed an ingress capability called routes. Kubernetes upstream liked it, patterned a new project called Ingress after it. They were not quite in feature parity state. There were still a number of things with routes, and still to this day, that provide advantage over Ingress. However, of course, we want to be more Kubernetes aligned, and our customers want us to be as well too. So we were faced with supporting both routes and the upstream Kubernetes Ingress, but we are contributing pretty heavily in a leadership role to Ingress v2 in hopes that will unify the different forms of Ingress, and we can make sure that we close some of those feature gaps. And I think other than that, one really, really big way that we contribute to the networking story in upstream Kubernetes is something that I was reminded of yesterday by yet another example, which is there are a number of times in upstream Kubernetes network development where the developers are hard blocked on either developing a feature or optimizing it or debugging it or solving a bug without strong contribution from the Linux kernel side of things. And this is where we uniquely can contribute on a somewhat weekly basis to unblock these kinds of problems. Yesterday, I believe the problem that was presented was solved literally within 30 minutes with a contribution from a Linux kernel engineer to enable things again. So it's that full stack-wide support that we bring to upstream Kubernetes. This is also another big contributing area. Now, more than having a leadership position, right? So, what's driving the things that we actually work on? Well, of course, it's customers. It has to be, right? So customers, they communicate their use cases to us, and together we partner and we identify what are the feature gaps between what's capable today and what are their requirements. And so everything that we do, my roadmap is filled with things that came in from customers to close some of those gaps. So I can't really talk about how it is we're advancing Kubernetes networking without talking about some representative examples of how it is that we're expanding networking capabilities through some of these feature requests and enhancements. So I can roughly break it down into about 4 different themes. The first three, these are givens. These are things that are must-haves. These are things we've always done. Got to be stable. It's got to be secure. It's got to be performant. It's got to be scalable. That's the nature of Kubernetes. And we have to keep driving these new features and close the gaps. Underneath each of those, I have some representative examples. I'm going to go through several slides that talk about these in more detail. So I'll come back to those. I do want to talk a little bit about the fourth category, though, and I don't want to diminish this one, but I do want to say the telco enablement is actually a relative newcomer. And let me qualify that by saying that we've been working on telco use cases for several years now, but that's Kubernetes and that's OpenShift. I would say that Red Hat as an organization has been addressing telco enablement for much, much longer, many, many more years than that, through other products. So, for example, enablement of 3G, 4G telco networking on top of OpenStack infrastructure, that's been around forever, and we've played a huge part in that development. The relative part here comes in terms of Kubernetes-specific enablement for telco. So I'm going to talk more about some of the foundational capabilities that were communicated to us, the things that they identified as initial gaps, and what we've done to solve those things along the way. We are, I don't know if any of you attended KubeCon last fall, but at that conference, Azar Saeed, a Red Hatter, he demonstrated an actual 5G deployment using Kubernetes technologies in container platform, OpenShift container platform. But some of the things that he used, admittedly, were using developer preview or technical preview features. And so we continue to drive those so that we can support them end-to-end and close any remaining gaps. So without further ado, let me jump into some examples of some of the work that we've been doing. Again, this is not an exhaustive list by any stretch of the means, but these are just some big things that we've done. So first of all, you've already heard the story of operators, I hope. Operators with regard to networking is no different. So the idea is that you have this container that runs 24/7 on the platform. It's a subject matter expert for one thing, like, for example, our cluster network operator, or maybe one of your applications operators, or maybe more specifically, a CNF, a container network function operator. And that operator is going to provide a certain level of stability for your particular application or that particular service on the cluster by being able to, depending upon the level of sophistication and maturity of that operator, it will certainly be able to do simple things like install and update and patch, but more advanced things are to potentially rebalance that across nodes, or to, if you've hit some predefined heuristic defined in the operator about what is a really high load level, the ability to potentially automatically scale out or up your cluster to meet the need. So this is definitely, in addition to the rest of the OpenShift container platform and the networking space, this is also equally important. Traffic isolation. I get a lot of customers asking me questions around this, or asking for feature enhancements here. And they kind of are broken down into one of, I guess, maybe three categories. The first category is that of, I want to be able to separate my Kubernetes control plane traffic from my data plane traffic. And the other one I get is, I want to be able to separate that traffic into via software-defined methods. But I also, maybe another customer would ask, I need to separate that traffic. I need physical separation of the traffic. Maybe I have two competing clusters on my, two competing competitors, customers on my infrastructure that I'm providing, or whatever. So we had to provide this kind of capability. And so what this played very nicely into one of the things that solved a number of other feature gaps or use cases that we had, which was the ability to have more than one pod interface per pod. So this came out of, as I mentioned previously, we led the upstream, as part of the Kubernetes networking SIG, we led the networking plumbing working group with all those 17 plus vendors. And and after about a year's worth of contributions, we came up with a really good specification for how it is we define these additional interfaces. And I'll talk more about this in future slides. I'll come back to it more. But I want to say that this played out very naturally here. So Kubernetes, as it is today, sends all of its control plane traffic across whatever the primary interface is on the pod, in this case, ETH0. And that's going to go out whatever network interface card on the host has the default route of the host. So if we call that network card number 1 as diagrammed here, what we can do is we can actually spin up a secondary interface, like say net0 in this case, and we can do a couple of things with it. We can actually use another thing that we developed, which is NIC partitioning, and we can actually divide the traffic on the NIC between 2 different traffic flows, or interfaces, in this case, ETH0 and net0, and they could potentially go to 2 completely different networks. Another thing we could do using that avenue. Another thing we can do, another thing we developed was a VLAN capability for these different interfaces, so we could software separate them using VLAN tags. And finally, the last thing that we can do is just throw another network card in the host. So, for example, if somebody wants that physical layer of separation, tie a secondary data plane interface, like say net1 here, to a completely separate NIC, and that's our best reasonable effort at separating physically the traffic.
So question here on
Sure.
Performance. One of the challenges that we go to a higher level challenge with Kubernetes and pinning processes to CPUs, et cetera, one of the things that we need in network frontend virtualization is the access to protocols like DPDK, et cetera, to accelerate performance. Have you guys addressed some of those challenges in OpenShift yet?
Yeah, that's a great question. I am going to talk more about some of these in upcoming slides, but let me preface them now to answer your question by saying, yes, we do have high performance solutions. We do have, for example, SRIOV. We do, in fact, have DPDK for SRIOV. We also have other networking solutions, like, for example, I heard some of that conversation with, I think it might have been with Fabian, about some of the VM networking traffic that was going on. If you're running pods in a VM, it may be advantageous to you to use the MAC address of the VM. And so what we can do is one of the CNI plugins we have that you could tie to one of these interfaces is an IP VLAN capability. So you could have, for example, net1 could be delivering traffic to the rest of the network via the MAC address of the VM. There's a number of things that solves. So there's a lot of flexibility you can do here. Once you have the basic fundamental capability of first of all, adding additional interfaces to a pod. So this was something that the original Kubernetes developers didn't think was necessary, quite frankly. So we, of course, our customers correctly had the vision to express to us the need for that, and so we put it into action. But so it's solved by not only the additional pod interfaces, but it's solved by the basically the stable of CNI plugins that we fully support with OpenShift Container Platform. And we're creating new CNI plugins all the time. So I mentioned a few there: IPVLAN, SRIOV. We have MAC VLAN, we have host networking, there's Bridge with VLAN, there's all kinds. And in fact, I'll talk about some third-party vendor CNI plugins as well coming up here.
Hey, Mark, real quick before you go on, I don't know if we covered this portion or if it's pertinent to the conversation or not, but does the platform in what you're talking about, do you guys natively support routing protocols down to the cluster nodes itself, or are people using things like FRR and things like that they're putting on the host to provide BGP or anything down?
Yeah, so depending on how you have the interface, depending on how you have the interfaces defined, and
right.
If you have a compatible card for it, et cetera. Yeah, so that's actually it's a bit of a rat's hole. I could probably talk about that for a very long time. I think in the interest of time, I just took a look at my clock.
Okay, no, you're good.
If maybe you and I could talk about that offline a little
Sure.
bit more, that would be great.
Awesome.
But yes, I'll answer briefly by saying, yes, we do have that capability with caveats.
Okay, fair enough.
So, all right, so let me advance on here to metrics, alerting, and telemetry. So one of the things the customers also have been asking us for is the ability to, let's say they did have an SRI interface with all this high performance going on. They want to be able to, obviously they're interested in high performance, so they want to know, how do I measure that? If something's wrong with my SRIV connection, how can I be alerted to that? How can I get telemetry from that? And I'm going to talk more about some use cases that are using this kind of thing. This really kind of revolves around our operator story. So the operator lifecycle manager is enables the ability to basically report things like the name, version, the channel, the health of the particular thing for which it's a subject matter expert for, like say a network like SRIOV. It also has the ability to fire off alerts, especially if that operator transitions into, say, a failure state. So these things are very useful. If we get, and these are telemetry is entirely optional. You can configure it any way you want. If I do recommend it strongly to customers, unless they have a real use case that says, no, I cannot send this telemetry back, this anonymized telemetry back to Red Hat. One big reason, quickly, is they, if Red Hat sees from some of its customer clusters this anonymized data coming in, and some of the numbers look a little bit off, but not too crazy, that may or may not trigger somebody. But if 70% of our customers' clusters are reporting these odd numbers, that's reason for Red Hat to raise the alarms, look into it, and potentially solve the issue before it's ever experienced by the customer. So it's actually very useful information.
So this is information that I really, really am interested in from a multi-cloud scenario.
Yes.
If I'm running pods inside of my EC2, Azure, and Oracle Cloud instances, can you guys, or is it on the roadmap to help me extrapolate how to do workload placement based on that telemetry data? So if I have noisy neighbors, et cetera, if I'm closer in latency to a service that I want, can Kubernetes and these.
Well, did I lose the audio?
That was cool.
I thought you were asking me about that object 10 times in a row, but are you still there?
Yeah, I'm still here. I don't know why it does. My video does that every now and again, but my audio does that every now and again. But yes, can you help me surface that telemetry data to help me with workload placement?
Yeah, so this telemetry data is not just for Red Hat consumption. You can consume this yourself within your organization as well. So an interesting thing about this is, depending on the level of sophistication of your operator, you can actually build in heuristics about what's happening and what you need to do. But like you said, you might need to have some understanding of what's happening in the rest of the cluster to determine, well, I want to expand my particular thing. Like maybe you've got an application that requires an SRIOV enabled NIC in the host. So you don't want to get bounced to a node that does not have one of those. So there is a number of Kubernetes constructs and projects having to do with, for example, labeling resources. And then you can identify, when you run your job, you can say, yes, run it, but only run it on nodes that have the following labels. Maybe one that has this much memory, one that has this many available cores, one that has an SRIV enabled NIC, and so on. And so you can build that intelligence into your operator as well as your application, but the operator is probably kind of a natural place for that. So yeah, the short answer, yes, that capability is there depending on the maturity of your operator. I'm going to move on now to security enhancements. This is almost a little silly having just two things on this slide, because I think back to all the things that we've done to enhance security, but these are two really good representative examples, I think, of the things that we've done upstream. So one of those things is Global Cipher Suite Configuration API. So we have a number of customers, especially on the financial market side, health industries, where they have regulatory compliance policies that have to be met. So for example, their policy their audits may raise red flags if they see TLS 1.1 or something in the list of ciphers accepted by the English controllers. So what we did is we enabled the ability to configure that to meet the goals of your regulatory policy. Another thing, network policy. So we've done a lot of that's an upstream thing that was started. Actually, I believe Tigera was the one who initiated that upstream. But there's been a lot of community enhancements to network policy. One of those things that we did is something called Network Policy Firewall, and what that provides is it enhances the egress object of network policy to say what our customers really wanted. Everybody likes the idea of network policy egress, the ability to filter egress traffic leaving the cluster based upon some rules that you define. What they discover pretty quickly is that that's something that can be configured by any developer or project admin on the cluster. And that, generally speaking, across all of our customers, is precisely not what they want. What they are asking for is that capability, but configurable only by a cluster administrator who is going to determine what types of egress traffic is going to be allowed from that cluster and to what destinations. So there's a lot of things like this that we've done to enhance sort of the defaults per our requirements of our customers. We brought up SRIOV, so let me talk a little bit more about that. So SRIOV, I mentioned it in the framework of an SRIOV CNI plugin. So you plug in this CNI and everything's happy. Well, that's not exactly true. There's actually something else you have to do. You have to enable an SRIOV device plugin, which is part of Kubernetes device plugin mechanism to configure that SRIOV capable card. And you have to do that in conjunction with the SRIOV CNI plugins configuration. And so there's an orchestration of events that has to happen there. It's just complicated enough and just error prone enough that we don't want to make you do that. So what we have, for example, amongst all of our other operators, is if you were to go to our OpenShift marketplace and look at all the operators we have in our user interfaces built-in operator hub, one of those tiles that you would see inside there that you could select is, in fact, the one that's shown here in the lower left, the SRIOV network operator tile. When you click on that, it comes up, it says, okay, here's a couple things you have to do. Here's some information about what's going to happen. And then when you say go, it allows you to set a few minor things in the configuration at that stage. But otherwise, what it does is it simply deploys on SRIOV supported cards a working SRIOV deployment. And then you can season it to taste from there. But literally inside of 30 seconds, you're going to have SRIOV deployed on your cluster. So this is exactly what operators are great at. And then not only that, it doesn't just leave you hanging. It sticks around and ensures the health of that setup as well too. So this is another thing on the performance and scale side. Another thing on the performance and scale side is we got customers saying, hey, that SRIOV, that's fantastic. You're able to move traffic. There's literally nothing faster, no faster way of moving traffic from the pod to the wire on my host. It bypasses Linux networking, the network stack altogether. So we're pushing packets directly to the card. That's fantastic. Well, guess what? My use case is that I want to stream data to clients. Well, in traditional Kubernetes, there's been support for multicast, but this multicast support was really low bandwidth multicast, designed around, for example, if you had several JBoss servers and you wanted to communicate their configuration between them, you could use that multicast capability to do that, but not high performance. It would fall on its face if you tried. So what we did was we enabled high performance multicast and developed that and contributed upstream as applied to an SRIOV interface. And we have a number of customers using this in production today, very happy about it.
So can you talk to us about where, I'm sorry.
That's okay, go ahead.
Can you talk to us about where the bottleneck is in the system today? Is it the ability to pin these processes to CPUs? Is it the PCIe bus? It's the
multicast. It's the multicast implementation itself. It just was not designed to be high performance. It was designed to be good enough to move configuration files from one node to another. Nobody ever tuned the way they did that. It literally, if you're sending, probably kilobytes of traffic would probably be its higher end of what it's capable of. And so it really was just somebody got something working somewhere. So we went in and we made it enterprise strength, and we fully support that end to end. Another thing, so we have a lot of customers that are doing AI/ML, and they have all these fancy nodes with expensive GPUs, and they want to be able to take advantage of this additional horsepower, not only to compute things on the node itself, but they want to move those packets around. So this is where we developed GPU Direct RDMA, so that you can push packets from one node to another as fast as possible. We have RDMA over Rocky today, RDMA over InfiniBand, quote unquote, tomorrow. So the InfiniBand development is on our roadmap. So there's lots of things happening there. In the interest of time, I'll keep moving along. Another thing is HA Proxy, our default ingress router. We have moved to HA Proxy 2.0. This in and of itself represents a huge performance gain for our customers. In fact, I had one customer that communicated to me that just the sheer raw number of requests per second they could handle was increased enough that they were able to reduce the number of nodes required for their servicing their application, able to reduce the number of nodes required by half. So they could reduce it by a factor of 2 because of the improvements in HA Proxy. I'm not claiming everybody will see that same performance improvement and possibility, but it's certainly optimistic. Multi-cluster. Very briefly going to talk about this. Hopefully all of you had a chance to catch a presentation about our Advanced Cluster Manager, ACM, and where we're going with that. That's really what this talks mostly about. So today, the communication between the different clusters is really via the hub using the Kube API service. But we have on our roadmap, and what's currently being developed right now are some proposed solutions to improve that networking capability. Essentially what we want to do is we want to have this secure layer 3 connectivity between all of the different clusters that is agnostic to the network being used on them and provides this ability to have services across clusters instead of just confined to the boundaries of a single cluster. So this is where we're going. This is something that we're pursuing. If you're curious, this is based on the Submariner technology, and this is something that we're furthering the cause of. So speaking of other projects, so let's talk more. Let's switch gears now to some of the features. So in this particular case, I want to set one thing straight right out of the gate, and that is we are not trying to solve 100% of the features for 100% of the customers. That's just not realistic. So what we do try to do is, it turns out, fortunately enough, there's about, we can solve about 85% of the features for the bulk of our customers. And so that is what you get. That is our goal for our default out-of-the-box networking solution. Anything that falls outside of that boundary, that remaining 15% or so of features that people ask for, that's where we rely upon our third-party vendors to fill the gap. So we have our default SDN. We also have, and so this chart is basically showing a bunch of different CNI plugins that we have available for Kubernetes to provide networking, the default networking for an OpenShift cluster. On the far left, we have the OpenShift SDN. That's our default today. Right next to it is OVN, which I'm going to talk about. That's currently in tech preview, but that's our next generation networking. On the far right-hand side is Courier Kubernetes. So for those folks that want to collapse the stack of networking between their OpenShift and their OpenStack to OVS-based implementations, what Courier Kubernetes allows them to do is basically pass CNI requests down to the plugin in Neutron. So that essentially it's Neutron that's providing the configuration of newly instantiated pod interfaces. So that's a possibility, and we also support that. But getting back to our third-party vendors, We have all of these vendors listed here, Tigera, Cisco, VMware, Juniper, Nuage. They are fully supported and certified in OpenShift 3. OpenShift 4, we added some new things, new requirements. The two key new requirements are that the containers that make up their solution must be certified. We need that so that we can work with the particular vendor to solve the problems, as well as provide reasonable assuredness to our customers that they're getting a secure container and not something somebody pulled from the internet somewhere that might have a security issue in it already. So we provide this reasonable level of assuredness with that. The other requirement we had for them was they must have an operator for their network. So we want them to play nice with the rest of our operator ecosystem, not only for the benefit of the cluster, but for the benefit of that particular networking solution as well, too. So when OpenShift upgrades, or if the networking solution upgrades, there's a reasonable, sane procedure for doing that, and a fallback procedure if things go wrong, and alerting and metrics and all that. So you can see here that today, thus far, the only third-party vendor that has fully certified is Tigera's Calico. And so they are fully supported end-to-end on OpenShift. We are very close with a couple of others. We're very close with Cisco ACI's CNI solution and VMware NSXT's CNI solution. If some of the problems are technical, some of them are just simply logistical, getting it through the machinery that is these organizations, including ours. And then probably closely followed by Juniper's Contrail and Nuage. So look for these certified solutions very soon.
So does this mean, like with a Cisco ACI or an NSXT, there would be a standalone operator for each of those, or would there be multiple operators within an ACI or an NSXT?
There would be a standalone operator for which for example, the Cisco ACI CNI plugin, it would be a subject matter expert for that particular plugin. And it would handle whatever level of, again, there's different levels of maturity and sophistication of operators. So whatever the operator was capable of, it would handle that for ACI. Now, Cisco ACI is a little bit of an odd one in the sense that you can do a couple of things. You can actually give more control to the OpenShift side of things to manage the ACI plugin, or you can actually relinquish control and hand it off more towards the ACI ecosystem and the rest of the data center environment, and have it assume more control for things. So it's a bit of it's up to the customer what they want to do, and we don't block them from doing that. We want to help them do whatever is necessary.
Thank you.
So Mark, real quick on the ACI piece, just to clarify, you're saying I can use the native Cisco ACI management plane to manage the networking stack on the OpenShift side, right? Or vice versa.
Correct.
Okay,
yep.
Cool.
Yep, you can do as little or as much as you want to do.
Okay, thank you.
Some other features, IPAM, so IP address management on these secondary data plane interfaces. We've configured it so if you have a DHCP server, you can use that to configure the IPs of those. If you don't have one, we provide a CNI plugin, which is sort of a mini DHCP server, which is specific to providing IP addresses on the secondary data plane interfaces. Or you can just keep everything static and just define things in a list. As I mentioned before, we're pushing very hard in IPv6 dual stack upstream. And finally, we're doing things like, for example, I've got a lot of customers asking for more control over their DNS queries. So one of the first steps that we did was we enabled DNS forwarding so that if there's a particular zone they want to be forwarded to their own maybe pre-existing DHCP server, which might be across a VPN connection in their data center, back at their on-premise data center, we enable that. So they pick the zone, they forward it to the DNS server or servers, and the next step to that is to then that we have as a proposed feature is the ability to manage those external DNS servers as well. Multi-network, I think I've kind of hit upon this one already, but just for clarification, essentially Kubernetes only has allowance for a single container network interface plugin. That's a severe limitation because, again, as I mentioned, and as you've seen examples for, our customers are demanding more than one interface per pod for certain use cases. So what the solution is we partnered with Intel. Intel started a project called Multus. We partnered with them, and then again, working with the Network Plumbing Working Group upstream in Kubernetes SIG, Network SIG, we developed and productized Multus CNI plugin, which you can think of as essentially a multiplexer. So it still is presenting a single CNI to Kubernetes, and Multus is handling the details of all the additional CNI plugins behind the scenes. And so essentially you feed Multus custom resource definitions, one for each CNI plugin that describes how what it's all about and what plugin is to be used. And then it just simply says, okay, any newly instantiated pods will get this interface. And so with these CNI plugins, we talked already about some of the different ones that are available. You can add new networks, you can add new capability to networks. There's all kinds of things you can do from there. So this really opened up a lot of doors. Another new feature thing, platform native support. So it used to be that our networking ecosystem was limited to just that of the cluster itself. But when we do installer provision installs on cloud platforms like, say, AWS, as depicted here, we're no longer dealing with and have to be concerned with just that of the cluster and what's inside. Now we have new elements that we partner with the cloud provider on. Like, for example, we need to make sure if we're setting up more than one availability zone in AWS for a customer, we need to make sure that that's balanced using AWS's native ELB. We also need to make sure that DNS is being provided by Route 53. Of course, there are going to be corner cases where customers have private clusters where they don't want to use those. And so, that option is supported as well. All right, now we're clicking gears here to telco, the last big section of this. So telco enablement, 5G enablement. As I communicated to you before, there's a lot of things that the telco community told us they required. They said that we really love the innovation of Kubernetes. We love all the features of it. We love the capabilities, the performance, et cetera, but there's a lot of gaps. If we're going to use this for our next generation 5G deployments at the far edge, we need some help. And so this is where they employed Red Hat to come in and take on these challenges. And thankfully, with our leadership role in upstream Kubernetes, we were able to solve most of them in a fairly short period of time. There's a few that have been added to this list since that initial list. But what you're seeing here is those obviously with a check mark. Those are things that are done. We've already done those things to satisfy the use cases for the telco 5G at the far edge or at the core. The ones with a wrench on them, we're somewhere in the middle of solving that. So a few of these, as I look at them, we're actually super close to solving. So just I want to give you some idea that, and then there's some that are actually a little bit further out. So like real-time processing, for example, that's one that is a longer-term goal that it requires a lot of interaction between not only all the elements of Kubernetes, but OpenShift and also the operating system itself. We do have some serious progress made there, but it's still going to be a little while. So one of those big challenges for our telco vendors is CNF onboarding. So there's several elements to do a CNF onboard. So one of those is OpenShift certification. To certify CNFs, we just make sure that it's cloud native to begin with. And second of all, we do things like make sure they're not running it as root. And if they do need escalated privileges for some reason or other, we make sure that it goes through a security review and maybe provide alternatives. Another thing is the portability. Of course, we want this to be portable across many different environments. So we have requirements that it be built on either RHEL or RHEL Core OS for the operating system. We have our universal base image for container images. Lifecycle automation. This is all about the operators. This is building an operator for a CNF, so it works with our advanced management and lifecycle capabilities. Storage, make sure they're using a OpenShift supported storage endpoint. This is all the fundamental basic ones, iSCSI, NFS, ones having to do with, for example, OpenStack, Cinder, OCS, and even the cloud providers themselves. So making sure that it works with vSphere, Azure, AWS, GCE storage options. Performance tuning. Basically, we want to validate their CNF on a production-like cluster. And we have a wealth of experience about how to performance tune CNFs. So we want to just provide the option of a review stage where we can present options like maybe you should use the node tuning operator, maybe you should use CPU manager for CPU pinning, maybe you should use huge pages, etc. So we have a number of, we have sort of an advisory role there. And finally, the same thing is true for CNF security. We published a white paper called The 10 Layers of Container Security. We have container security best practices guides, and we want to serve as in an advisory role there as well. Host level features, as I mentioned already, the fact that we're an operating system company as well provides a huge advantage to providing some of the telco enablement features that are required, that are really more on the side of the host solving it. So for example, when you're communicating with a radio access network, the tower, you want to make sure that you can do that. You have precision time protocol for the super accurate timings, and you want real-time capabilities so that you have guaranteed completion times. SCTP for multi-homing, node tuning operators, node feature discovery, node topology manager to provide NUMA capability, CPU manager for CPU pinning. These are all things that are really host level, but interact with, in a very deep way, the cluster itself. Platform integrations. I'm hoping that everybody here is already fully aware of the different modes we have for our installer, the full stack automation versus the pre-existing infrastructure. If not, we have sort of a mapping here for our 4.4 release of OpenShift. We also, on the left-hand side here, what I want to press upon you is we heard loud and clear from our telco vendors that the cluster footprint that we require today in the data center is fine for them. But when you get to the far edge, that's not going to work. They need something smaller, so a smaller footprint. So what we've done, and in fact, it's in tech preview today, is instead of requiring, as shown here, the 3 red boxes representing the 3 master nodes that are required for any cluster, plus the black nodes there representing the worker nodes, instead, we want to combine those together and create and support a 3-node cluster where you have your 3 masters for high availability, but we will also support placing workloads on them. And then, so that's tech preview today. We're targeting the fall timeframe to support that more completely. And then the last step will be the ever elusive all-in-one. So we want this all-in-one Kubernetes cluster essentially or Kubernetes deployment to run at the far edge. And for that, we're looking, we're moving into the next calendar year to solve that one. And the last thing I want to talk about, OVN, very briefly. I know I'm very close, if not over my time here. So very briefly on OVN, why did we choose OVN for our next generation? There's actually a lot of reasons. A few big ones are here. So first of all, we already have this proven Red Hat leadership in upstream OVS and OVN communities. Also, our current networking solution is really primarily Red Hat owned. So that's not a good place to be when you're an open source organization. You want community around your projects. And so going to OVN, we're going to get that community. There's lots of organizations that are active participants in the development of OVN. Also, we want something that's a more modernized architecture. We want something that has this flexible architecture, more modernized programming languages and programming styles, et cetera, more agile, so that we can develop features that our customers ask for much faster. And finally, another big one is our OpenStack product already has OVN as an option. Our Red Hat Enterprise Virtualization is already defaulting to OVN for the networking. So we see this as a consolidation of efforts across our products and engineering to provide this one project, OVN. And just to provide a level of comfort for everybody, this is not a massive change in networking. So if somebody says, wow, a whole new network, how do I plan for this? What do I have to do to prepare for this new networking? Generally speaking, there's not much you have to do. Let me explain. Most things, if you put them side by side, they're either exactly the same or they're effectively the same. The way OVN Kubernetes does things is ideally more performant and more flexible. I think the one thing that I would have to communicate to folks to prepare for oven, or as we call it, or OVN Kubernetes, is that we are moving from VXLAN tunnels to Geneve tunnels. But so far, this has not been a problem with the customers that have been exploring the option. There's plenty of Geneve offload capability between some of the vendors. We work with Mellanox, Intel, and other vendors to make sure that Geneve offload capability is built into their cards. So this has not been a major issue, but it's something to be aware of and explore in your environment before going to OVN Kubernetes. Oven.
Can I ask why you moved to Geneve instead of VXLAN when VXLAN seems to be pretty much the standard in the data center for part of the overlay?
Yeah, that's a really good question. So one of the things is we can build in some extra features into the Geneve headers that were not possible with VXLAN. There were also some other competing VXLAN-like overlays, like SVGRE and some others. So what Geneve does is it's capable of doing the things that all the other overlays can do, including VXLAN, but it has extra capability. Like, for example, I can build in IP address information, and in doing that, extra IP, and so I can use that potentially for filtering or redirecting or providing routing, decisions and so on. So Geneve is suited to be far more performant and flexible. So that's the primary driver. Now, Geneve happened to be the default for OVN. So it's not like we changed it in OVN from VXLAN to Geneve. We took it and ran with it, is really what happened.